Okay, well, welcome to two-sample inference for the difference of means. In the last few lessons, we were looking at separate data points, and specifically two separate data points, collected on either the same individual or the same pair. We were looking at one sample of the differences. But now we're looking at two independent samples and the difference between the means of those samples. So there's a key distinction there. And it might be a bit confusing to tell and distinguish the two types, but just remember, am I looking at the average difference or am I looking at the difference of the averages? So our first type of inference technique, or two-sample inference for means, is going to look like the two-sample t-interval for the difference of means. Again, I'm trying to estimate the difference of two population means. So we will still follow our state plan do conclude, as well as our panic model. In our state, we will mention the parameter that we are trying to estimate. We want to estimate the true population difference of means between, yada yada. We'll check our assumptions, and again, these are not changing. You'll see that they have been the same since our first time with inference back in Unit 5. Well, we're looking at random condition here, and I want a random sample so I can generalize to my populations of interest. Or if I use random assignment, I can infer cause and effect from one of the treatments. I then want independence within each sample by checking my 10% condition, and if and only if I'm sampling without replacement. Next, I'll check independence between my samples by seeing if they came from separate data points, separate locations, separate times, but something that indicates to me that population 1 will have no influence on population 2, which in turn means sample 1 has no influence on sample 2. And then lastly, we will check our normality condition, and it's not going to be normal by large counts, but instead normal by one of the following three. So we have to check both populations separately, and either both populations are normal, either they have, and if that's not the case, then they might have a sufficiently large sample size, which then allows us to use the CLT, or we might have to graph both pieces of sample data, so that way we can see if there's any evidence of skewness or outliers so that we have a pretty symmetric distribution. Now, this normality condition isn't about the population. It isn't about the sample. We make the normality condition about the sampling distribution. If our conditions are met, we will use a two-sample t-interval for the difference of means. My interval calculation, again, is going to look like my point estimate or my statistic. Here, x bar 1 minus x bar 2 estimates the difference between mu1 and mu2. And then I have my critical value, and then I have my standard error. Again, this is a standard error because it's based off of the sample standard deviations. My critical value, now, it gets a little tricky here, and we're just going to rely on the calculator to do the degrees of freedom for us, but we are going to make a note to the reader. And the reason being, if we use a conservative margin of error, while that's an okay practice, we're going to rely on the technology here to ensure that we are as close to the estimate as possible. And lastly, in our conclude step, we are this percent confident that the interval from blank to blank captures the true population difference in the means. And then also, since we're looking at confidence intervals with two separate groups, we have the following. We could talk about the confidence level, which is the repeated sampling and capturing the difference of the population means. And based on our interval, well, if 0 is in the interval, the only way 0 can be in the interval is if the two means are the same, thus meaning there is no difference. If 0 is not in the interval, we have some evidence that there is a difference, and that just depends on how the difference is defined and whether it's mostly completely positive or completely negative. Okay, so let's take a look at a very fun example from 2009's AP Statistics exam, and we're looking at FRQ number 4. Now, I will comment on the fact that typically hypothesis testing is the more common inference procedure that you will be using on the AP exam, but it could happen that, they throw us a curveball and we decide to use confidence intervals. Nonetheless, you'll be prepared. Well, here I'm looking at one of the two fire stations in a certain town responds to calls in the northern half of the town, and the other fire station responds to calls in the southern half of the town. One of the town council members believes that the two fire stations have different mean response times, and the response time is measured by the difference between the time an emergency call comes into the fire station and the time the first fire truck arrives at the scene of the fire. Data were collected to investigate whether the council member's belief is correct. And a random sample of 50 calls selected from the Northern Fire Station had a mean response time of 4.3 minutes with a standard deviation of 3.7 minutes. And a random sample of 50 calls selected from the Southern Fire Station had a mean response time of 5.3 minutes and a standard deviation of 3.2 minutes. Let's go ahead and construct and interpret a 95% confidence interval for the difference in mean response times between the two fire stations. Alrighty, so in my state part, I want to estimate mu1 minus mu2, where mu1 is the true mean response time of the Southern Fire Station, and mu2 is the true mean response time of the Northern Fire Station, and I'll do so with 95% confidence. Now, Mr. Pinto, didn't the North Station come first and then the South Station? While that is correct, and it does not matter how you define the difference, what matters is that you stay consistent with the difference. If you decide to do north first minus south, you'll get the same standard error. It'll just be your difference of means that will be different. So here I just opted for the one that had the larger mean so that I could see that my difference was positive. Okay, so in my plan step, I'm going to talk about what I was told in the problem. And I know that the Southern Fire Stations, because mu1 is the south, we have 50 calls with an average of 5.3 minutes and a standard deviation of 3.2 minutes. And the Northern Station had 50 calls as well, with an average of 4.3 minutes and a standard deviation of 3.7 minutes. Now, since I used random samples of 50 calls from both stations, I can generalize to the populations of each. It's reasonable to assume that both populations have at least 500 calls. It's also reasonable to assume that the samples are independent of one another since they came from separate stations. And lastly, our normal model is appropriate for both stations by the central limit theorem since we have a sufficiently large sample size. Since our conditions are met, we will use a 2-sample t interval for the population difference of means. Oh, I made the cardinal sin. This right here should say the population difference of means, not the mean difference, because I'm looking, is there a difference between these two groups? Okay, in my do and conclude step, I get the degrees of freedom obtained from the calculator. I'll show you how to do this because there's a nasty formula to get the degrees of freedom when there's 2 samples involved. And here, I'm just going to give the formula for my interval instead of showing all the work because it gets a little complicated with the t-star and the degrees of freedom. But nonetheless, I produced this confidence interval here, and I get that I'm 95% confident the interval from negative 0.3732 minutes to 2.3732 minutes captures the true difference of the mean response times from the Southern and Northern fire stations. So let's go ahead and pull up our calculators. And from the home screen, we'll go to Calculate, we'll go to Menu, we're in a statistics class, and we are using a confidence interval. Well, I used a 2-sample t interval for the difference of means, option 4. And I don't have the data, but I do have the statistics. And in my statistics, I had an average of 5.3 minutes with a standard deviation of 3.2 minutes and a sample size of 50 calls. In my second group, the Northern Fire Station, I had an average of 4.3 minutes with a standard deviation of 3.7 minutes and also 50 calls. Next, we're going to go down here. Our confidence level was 95%. And this pooled, we're going to ignore it. We're just going to say no. We're going to hit OK. And I get my same summary statistics. And what I'm going to indicate to the reader is the degrees of freedom right here. And I'm going to give a note like I did in my calculations that I got this from the calculator. And then I just pool the bounds. Here's my lower bound. Here's my upper bound. And we interpret it. And that would receive full credit on the AP exam. So that's a little bit on the process of running a 2-sample t interval. But here's the important part is the follow-up. Does the confidence interval support the belief that the 2 fire stations have different mean response times? Well, since 0 minutes is included within the interval, the confidence interval does not support the belief that they have different mean response times. The reason being, if 0 is in this interval, the only way 0 can be in this interval is if there is no difference. Thus, since I have some negative, some positive, this could be up to variation. I have evidence that there really is not a difference most of the time. Okay, so go ahead and pause the video now and look, I'll give you the answer to the first one. Pause the video, give yourself 5 minutes to look at this situation here and go ahead and just reference your notes, and then we'll come back together whole group to review the answers. Okay, so we look here at our cell phone durability. Would the results allow us to conclude cause and effect? Of course not. Random assignment was not used, so we cannot conclude cause and effect although we can see some correlation. Now, the conditions for inference, we took random samples. We have at least 10%. We haven't sampled any more than 10% of the population. Since we have separate manufacturers, it's reasonable to assume the samples are independent of one another, and our sufficiently large sample size will allow for us to use a normal model by the central limit theorem. Next up, when we interpret it, we are 90% confident the interval from 0.46 drops to 1.82 drops captures a true difference in the population means of the durability of the two phones. Does our interval support the belief that there is a difference? Well, yes, since 0 drops is not included within the interval. The confidence interval does not support the belief that there is a difference. Wait, why did I make the same mistake again? Wait, 0 drops is not included. Thus, we do believe that there is a difference, because if 0 was included, there would be no difference. But here, it does support. So go ahead and cross out this not. And lastly, based on the interval, which company has a higher durability? Well, the interval is completely positive, so we have reason to believe company 1 has a higher durability since the difference is defined as company 1 minus company 2. And since we're completely positive, we're greater than 0, we see that company 1 tends to be greater than company 2 almost all of the time. So that is a little bit more on two-sample inference for estimating the difference of the population means. And I made a few mistakes, so please forgive me. And just in case you forgot to capture those, right here the confidence interval does support because 0 is not in there. And then also in our previous example, when I named the test here, it should be for the population difference of the means. So I hope you will forgive me, but if not, no, actually you have no choice. So anyways, we're going to wrap up this unit looking at a two-sample t-test for the difference of population means. But this concludes our lesson on a two-sample t-interval for the difference of means.